Hi there. We're now starting a new section. We're going to be talking about processes, which is an abstraction provided by the operating system together with the hardware such that we can run programs in interesting ways. Okay? So we're going to start seeing what a process is. Then we're going to see how we create processes using operating system services. And then we'll see how we can do interesting things with processes. So what is a process? But first of all, why are we learning about processes? Well, because they are not abstraction in a computer system that provides this interface between the program and the underlying CPU plus memory. Okay? And this is provided by the operating system. Okay? So what do processes have to do with exceptional control flow? Well, the operating system is going to have to use tricks with exceptional control flow to give the illusion there are multiple processes running simultaneously in the system. Okay? So what is a program? A program is just a list of instructions, a collection of instructions and data that form your code, that form your software. Okay? A processor, obviously, is the piece of hardware that runs the instructions in a program. In a process, well, a process is an instance of a running program. When you start running a program, you create a process to run the program. Therefore, the process is an instance of a running program. Okay? So that's a very important idea in computer science, and it's not the same as a program or a processor. Okay? A processor executes instructions, and a program is a collection of instructions and data. A process is an instance of a program running in a processor. So, and they provide two key abstractions. The first one is logical control flow. So that means that each process has the illusion that it has full control of the CPU, as exclusive use of the CPU, which might not actually be in reality the case, but processes give this abstraction to programs that, so to processes such that it seems like they have full use of the CPU. Okay? And now the other one is private virtual address space. It means that this gives the illusion that each process has control over the entire memory. Nobody else is touching memory. Okay, so this is very important because it makes it much easier to isolate programs, to manage memory layout, and so on. Okay? So why are they important? Well, it simplifies writing programs a lot because you give the illusion that the program has the entire memory, and also gives it the illusion that it has complete control of the processor, complete use of the processor. Okay? And how are these illusions maintained? Well, first of all, process executions are interleaved. Okay? That means that from the processor point of view, it's switching between one process and the other. And the address space is managed by virtual memory, by the virtual memory system, which is going to be a topic of our next section. So processes can be concurrent. And it means that if they run concurrently, if the instruction flows overlap in time, otherwise they are sequential. So let me give you an example. Suppose that I have process A here, process A is running, having control of the CPU, and then now it's paused for a second, and it continues running, and it ends here. Okay? Process B starts here and ends here. Process C starts here, runs, pauses for a bit, and ends right there. So that means that processes that are concurrent are A and B are concurrent, okay? And also A and C, because you see they are actually running in parallel. However, B and C are not concurrent because B ends here right before C starts. Now, the user view of concurrent processes is as if they are actually running at the same time. Okay? That's the illusion that they have full control of the CPU, when in reality what's going on is that a process might be paused but still conceptually executing, but not really. Okay? It's not actually making use of the processor. So we can really think of concurrent processes as executing in parallel. Now how does that work? Let's say they have a single processor and you have multiple processes running at the same time. How does that work? We need some mechanism that bounces between processes that are running at the same time. Okay? So this is what we call context switching. Okay? So the processes are managed by a shared chunk of OS code called the kernel. Okay? And it's important to note that the kernel is not a separate process, but it's just a piece of code, a special piece of code that runs as part of a user process. But kernel code has special privileges. So here's how the context switch happens. Say that process A is running, and then suddenly its time based on a timer tick. There's a timer interrupt that says, okay, the processor time for process A, CPU time for process A is up. So now there's an interrupt here, time interrupt, that switches to kernel code, and the kernel code is going to save the state. You save A here, save the state of A, and then you restore B. And then B executes, then time's up again. The kernel code executes to the context switch, and the context switch saves B here and restores the state of A, and then continue. So that's a process called context switch. Now, what's actually saved here? Well, we have to save here. We have to save the instruction pointer because we have to know where process A stopped. So when it's restored again, it can continue executing from that point. And it also needs to save register state, okay? Because we need to restore those to continue executing the program. And there are a few other things that also happen there, but that's subject for another time.